Hi, everyone. Some of you had questions about the homework, particularly, I think it was like two, um, 5, and 6. So I'm going to go over an intro for each of those. So for number two, we have, like a track that people run around with some kids with different masses and in different lanes, meaning their radius is going to be different, but they're running with equal speeds. So for part A, we're looking at their centripetal acceleration. So we're looking at just v squared over r as an equation. And then part B, we're looking at centripetal force. So it's got, all the variables mv squared over r. So something that we can eliminate is the fact that they're all running with equal speeds. So we're not looking at the velocity. So for part A, we're only looking at the radius. So we can make the statement that the centripetal acceleration is going to be the inverse or proportional to the inverse of radius. So the bigger the radius, the smaller the centripetal acceleration. So we're not looking at the mass of the kid, of the runner. So the fact whether it's 4m, 3m, that doesn't matter. So the kids with the smallest radius will yield the biggest acceleration. So both runners A and D, they'll have that same acceleration because they have that same radius. So you can go through and rank them according to basically the radius. So you're going to have some ties because you have two kids in each lane. So if you look at the solutions in Schoology, hopefully that will help you to see why the largest and the smallest centripetal accelerations are ranked as they are. It's because of this relationship here. For part B, we're looking at centripetal force. Again, looking at equal speeds, but here both mass and radius are going to play a role. So we can make this statement that the centripetal force is going to be proportional to both the mass and the radius. So you're going to have to do a little bit of extra work for this one. So let's pick, I don't know, runner A. Runner A is 4m, or 4 times this initial mass, and then running on a lane that has 4r. So looking at that, in this relationship, it's going to be 4m over, where are we at here? 4r. So we're not really concerned with the m and the r. It's going to be the same for every runner. So we can kind of ignore that and just look at this as 4 over 4, so that's got a value of 1. So runner A would have a value of 1. So you do the same thing for each runner. So for runner, say, like B, so that was for, the blue was for runner A. We'll do blue for him or her. We'll go green for runner B. So the green has a mass of m, so just 1m. And in lane 2 or 5r, so again, the m and the r are consistent with each runner, so would be 1/5. So definitely runner A, which is the blue, has a larger centripetal force as compared to runner B, where it's 1/5 that of the other runner. So just dealing with proportions, and you just rank each runner and then go through and rank them in that largest to smallest. You're going to do a similar thing in 5. The difference here, we're still looking at centripetal acceleration and centripetal force, and we're going to use those ratios again. But in this case, the velocities are not the same, or velocities are different, but mass is the same. So for part A, we're looking at centripetal acceleration, so mass isn't even in that equation, so we still have to look at it as, a proportion of the square of the velocity, whatever it is, 2v, 3v, and the radius. But for the force, since all the masses are the same, we're going to ignore that part of the equation, and we can make the statement that it's going to be proportional to both v squared over r, which might give you a little hint for something. So the same thing, let's say we have, again, we'll do runner A, their acceleration v squared over r, so it would be 4 squared over 4 for their radius, so 16 over 4, which is 4. So they would have a rank or a number you can associate with them as 4. For runner B, we'll do B in blue. As far as acceleration goes, it's v squared over r. So v, 1 squared is just 1 over 5. So that would be, again, 1/5. And that's how you would rank each one. And then assign them a spot in that largest to smallest part. And again, seek out the solutions on Schoology if they're a little bit more detailed. And if still, this video doesn't help, reach out to me personally through Schoology, and hopefully I can make another video or give you some tips or tricks. For number 6, this is like that Gravitron ride. A lot of times they appear in carnivals. They look like a spaceship. You go in, there's music and lights, and you kind of stick to the wall. So that's a similar thing here. There used to be a ride like this in Wildwood, I believe, in New Jersey, where it was this was the floor. So this is where you would wait in line, and then you go in and you stand, and then this floor would drop out, and you would stick to the wall as you spin around. So that's the idea. So force diagram is definitely needed to analyze our scenario. So a force diagram for the rider. We got force due to gravity going down, and there's no floor, so it's not going to be a normal force, but it's going to be a force of static friction. So there's enough friction between him and the wall of the ride that prevents him from sliding down. So they're going to be equal. So then, depending upon where you think of this rider being, if he's on the left-hand side, like over here, there would be a force going to the right towards the center of, that ride, the center of that circular turn. And that's going to be a normal force that's provided by the wall. So the normal force is his centripetal force. There's only one force making it go in a turn. So you can kind of set up your equation for that, where it's going to be normal force. But what is normal force equal to? There's no other force going in the opposite direction. But we have enough information to use the Fun equation. So we do have a way of calculating the force of friction, and we're given mu. So we have the mass of the kid, so we can get gravity. That will be equal to friction, and then using the Fun equation, we're looking for normal force, so normal force is equal to force of friction divided by mu to get that. So you'll be able to eventually solve for velocity. So the question's a little weird. It talks about this period of rotation. All period of rotation means is how long does it take to go one revolution. So since time is hidden in velocity, that's what we're looking to solve. So once you get a velocity, so velocity fundamentally is distance over time, but the distance we're moving here is a circle. So the distance that something moves in a circle is circumference. So that's 2 pi r, which we're given the radius. Keep in mind that we know this number. We calculated it. And Capital T stands for period. So that's what we're looking for, the time it takes for that one circumference or one revolution. So you'll have that V, you'll have that, and you can solve for the time or the period of rotation. So again, take a look at the solutions on Schoology. Hopefully this video helped. If you still need some more help, send me a Schoology message and I'll get back to you with another video or audio, or maybe it's just some quick comments. Have a nice weekend.